you hear me? Hello? Do you hear me?
Yes.
Okay, thanks. Let me remind you what happened last time. So, okay, so we consider it induced maps. So we can start with map from topological space X to topological space Y. And then first it induces map F sharp between the corresponding abelian groups of singular chains. Map is a homomorphism between abelian groups, and of course, so we can define it on generators, and here generators are continuous maps from n simplex to X, and generator is just mapped to a composition of this singular simplex map with our function f, and then it extended by linearity to arbitrary chains. Then we have induced map between the corresponding homology groups. It was defined by taking a class or singular chain beta and mapping to the class or F sharp map applied to beta. So here beta is an element n of x representing some element in the homology group, and then we showed various properties of this push forward map, and in particular we started to prove the theorem which tells us that if you have a pair of homotopic maps from X to Y, then the push forwards are just equal. So there's the same homomorphisms. We started doing it by first considering some explicit homotopy between these pair of functions, capital F, and then considering this prism. And this prism was decomposed into a union of n+1 simplices, which with vertices given by the following sequence. So we started from V0, we go till Vi, and then we consider Wi, and then we go till the final vertex, which is Wn, where P and W, they denoted vertices at the top and the bottom of this prism. So in particular, delta n. So at the bottom, we had a n simplex with vertices v0 to vn, and top we had vertices from w0 to wn, and then we use this subdivision of the prism into n+1 simplices to define what we call the prism operator, which is space. So let me continue here. So again, this is just I repeat what already done last time. So then we use this subdivision to define the prism homomorphism from Cn of x to Cn+1 of y. And again, so we define it on the generators and then linearly extend to the full group. And so sigma, which is a singular n simplex in X, was mapped to following sum over I and here we consider a composition of F with sigma times identity map on the interval, and so this is again, this composition gives us map from delta n to y. Sorry, from delta n times interval y. And then we use, we can restrict it to a simplex, n+1 simplex inside this prism with vertices from v0 to vi, then wi till wn. And this restriction gives us map from delta n+1 to y, which is indeed a generator in this group. And then it was announced that we want to show the following property, that satisfied by essentially the statement about the commutator of this prism operator and the boundary homomorphism. Okay. So to show this, we will just again apply this. Let's start with the left-hand side. We apply it to an arbitrary generator, like here, for example, sigma. So so what we want to do is so we already have explicit expression of what is P of sigma, and then we need to apply to act by boundary homomorphism on this expression. So here, the boundary homomorphism. So we have to take a sum. Where in each term of the sum, we will want to remove one vertex in this simplex. So And of course, it is, well, since we have the following kind of expression for the vertices in our simplex, it's convenient to split the sum. So we'll start removing in this D, we remove J, let's say J's vertex. And there will be some, and there will be sum of minus 1 over j with this removal. So more explicitly, we'll have this sum over j, and let's first list all terms where j is goes before I, up to I, including. So we will remove this. Will mean that we will remove one of these vertices v. So there will be some. Okay, there is this weight minus 1 to the j. This comes from just definition of the boundary homomorphism. And okay, we will still have this minus 1 to the 8. So this is what we already had in the prism operator. Here, okay, so we want to remove j's vertex, which is vj here. And somewhere, so this will happen before this, we'll have the pair di, wi. And then there will be a sum of terms where we will reach, where we remove vertex, some of the w vertices. This we can write when j is greater or equal than I. So here so we'll do the shift. So this here we will start counting this. So j equals I means we are at this position. J equals I plus 1, we are at the next position. Since we kind of made a jump by 1, so instead of minus 1 to the j, there actually will be minus 1 to the j plus 1. The rest, this will be still the same. Again, as promised, here we remove one of the w vertices at position j. This is what we have. And now it's convenient to separate it into two terms in a different way. So let's separate it. Let's consider first term A, and this will correspond to sum of the terms with I equal j. So this will be, you get a contribution process from this and this when j equals I. And the second piece, which we'll call B, will everything else terms with I not equal to j coming from either of these two terms here, which we have here. Okay, let's deal first with A. Okay, we'll just we'll just start with this and just take only terms where j equals I. So there will be single. So we just take terms with j equals I, and we'll keep notation. We'll just use sum over I. So this, for example, when j equals I, this product of minuses gives you 1. And here, when j equals I, this gives you -1, right? So first, we'll have +1 times f times identity of the interval restricted to, so since when we have I equals j, means we remove, so we remove vi. After vi, we immediately have wi, and then we n. Here with -1. This piece will be from the terms j equals I, where we removed one of the w vertices. So this means, in particular, we'll have vertices v0, all vertices from v0 to vi, and but then we remove, since we take the term when j equals I, we remove wi, so we will follow immediately with wi plus 1. Good. But then you can see that this guy here, this term here, it's just essentially the same as here, just with I replaced by I plus 1, right? And this means almost all terms in these two sums over I, they will pairwise cancel with each other. The only thing which will be left is the first term here, which we won't be paired with anything, and the last term here. They are not going to be paired up. So in particular, the first term here is when I equals, okay, yeah, this corresponds to when we remove all v vertices. So this you have a composition. This composition restricted some subsimplex. They are all w's minus same thing, but restricted to the simplex where all vertices are v vertices. But this is what this thing. This is just our simplex delta n times the bottom of this prism, and this is delta n times 1, the end of our interval 0, 1. If we restrict here we have v vertices, and here we have w. So yeah, if we this restriction here is equivalent to, since we're considering 0 boundary of this interval, here we can restrict f. It's the same as restricting f to 0 and then just composing it with sigma. And for this first term, similarly, it's the same as restricting f to 1 to the end of the interval and then composing it with sigma. But now we recall that f was our homotopy between a pair of functions from x to y. So this f restricted to 1 is just our j. And g, which we still have to compose with sigma, And here, f restricted to 0 is just our f. Sigma. So what we get here, by definition, this is we get an action of the induced map on the on singular chain. So we can rewrite it. This is just a definition that is the same as G sharp of sigma minus F sharp sigma. So these terms, the collection of all terms with I equals J actually gave us already this result, this part of this identity which we want to show applied to our generator sigma, to which we plot here. So for the rest, we need to, for this means that for these terms, the collection of all terms with I not equals to G should give us this, the rest applied to sigma. So let's see how this works. Are there any questions so far? We consider terms with I not equal to G. We just can rewrite the same thing, but I mean, skip the equality part. Now we want to check if this B part is the same as this expression. So we first apply D on sigma and then apply the prism operator. Okay, let's just apply this definition of D and P on sigma in this order and see that it's indeed gives us these B terms. Okay, let's first apply the boundary homomorphism by definition. So this is sum over I, and here, well, for example, I choose my vertices to denote it by V with some index, and this means I skip vertex number J in the sequence V0 N. And then I apply the prism operator. Well, I can use linearity, so I can apply it to each term here. So how does this prism operator works? So prism operator works. First, we need to essentially, so instead of considering a simplex, we extend this simplex prism, and then we consider composition of F with sigma times identity on this interval, and then we consider restrictions to some sub-simplices inside this prism. But formally, you can just understand it by a kind of using the formula which we had. You replace bunch of the V vertices by W vertices, and you extend the length. And the length here of the sequence of vertices is extended by 1. Again, so at some point we will have to, using that formula, at some point we will have to start replacing V vertices with W vertices. And again, it will be useful to consider first when we do separately two kind of terms. One where we do this before this vertex Vj, which we remove, and the other term where we do this after. So first, if this happens before, actually, yeah, so here actually I use J. The sum is over J. And the place where I will start replacing vertices V with W, I will denote by I. The first part is where I is less than J. Still this sum over J carried over. You have -1 over J from here, and there will be, of course, -1 to the I. This is from the definition, the sign from the definition of the prism operator. And then when we apply the prism operator, okay, we do this composition of sigma of F with sigma times identity. And here we go till I. Then we continue with Wi. And here, okay, before we replaced, we removed Vj vertex, but since we started, we kind of replaced all vertices before this start from some point with W. We will now, this means that we remove Wj. And there also will be some for I greater than J. Again, there will be still -1 to the J. Just it over from here. And, there will be -1 to the I plus 1. This is a sign from the definition of the prism operator. And this, again, we have a +1. It's the kind of +1 jump compared to this part. This is because once we kind of go through this skipped vertex, we skip one position. Still have this composition, and now we restrict it simplex, where we start with V0, then we remove Vj, we go till Wi, sorry, Vi. This is, again, this is terms where we do replacement after this skipped vertex. And then we have Wi. Well, now we can just look at this. And also look at this, what we had before. And you see that, okay, this part, when J is not, when we skip the terms with J equals I, is exactly exactly this, right? With the correct sign, because we can, for example, we can remove this +1 here by the cost of having plus here. And similarly, this part, again, when we skip terms with j equals I, is just exactly this sum here, also with the correct sign. So indeed, we check that B is equal to this. Okay, and combining this with analysis for these A terms of type A, we indeed arrive at this promised identity, G sharp. You can rewrite it in this way. The difference between G sharp and F sharp is equal this sum of composition of the prism operator and the boundary homomorphism in different orders. This can be sort of the identity between homomorphisms from Cn of x to Cn of y. And yeah, as already essentially showed last time, from this it immediately follows the fact that the induced map on the homology groups will be just the same. This is just because, okay, let's consider some class in homology of X. This class is represented by some element in Cn of X, some singular n chain, such that its boundary is 0. Let's see what is F star applied class. By definition of the push forward, this is the same as class of F sharp of alpha. And then I can use this identity to rewrite it as a class of G sharp of alpha plus minus G, compose this P applies to alpha minus P composed with D applied to alpha. Well, this is 0 because the boundary of alpha is 0, and this is equivalent to 0 in homology. So the class of this is 0. So this thing is a class of G sharp of alpha, and which is by definition is the same as star applied to class of alpha. Concludes the proof of the theorem. Or it was proposition. Any questions? Okay, from this proposition, we almost immediately can show the following corollary. If you have F map from X to Y, which is a homotopy equivalence, then the corresponding induced map from Hn of X to Hn of Y is an isomorphism. So this is similar to what we had with the fundamental group, but the proof is actually easier once we showed the push forwards of homotopy equivalent. Oh, so push forward of homotopic maps are the same. Easier, the proof will be easier because in particular we don't need to care about this base point, which we needed to do for the fundamental group. Okay, so F is homotopy equivalence. This means, by definition, there exists G, a map in the opposite direction, such that the composition of F with G in this order is identity, is homotopic to identity. I don't remember how would you denote it. Homotopy, I think, like this. Important. Such that F composition of G with F is homotopic to identity on Y, and G with F is homotopic to identity on X. So the G is a homotopy inverse F. But it's from we can just okay. We already showed in last lecture that the push forward of the composition is the composition of push forward, and push forward of identity is the identity homomorphism. And so we can apply the correct push forward of both sides of these two equivalence relations using the proposition which we just showed. So for push forwards of both sides, we just get identity of the proposition, and using the properties of push forward with respect to the composition, we get the following now equalities of the conic homomorphisms. Homology group. Well, this means that we had some homomorphism F star, and this means that G star is its both left and right inverse. And this immediately implies that F star is an isomorphism. Any questions? So in particular, if you know, we can do if you know a homology group of some space, and we immediately know homology groups of the logical spaces which are homotopy equivalent to them. So in particular, we know the homology groups of a point, and we know that, for example, Rm is homotopy equivalent of a point, or you can also take, for example, a disk. And this means they all have the same homology groups. Zero, sorry, Z when n equals 0 and 0 greater than 0. So as you could notice, like when we consider this, when we proved various statements about these push forwards, like part of the statement, there was some part of the proof which was kind of involved indeed some topology considerations. We did consider some maps between topological spaces, but after some point, the proof became purely like algebraic, and we only relied on particular kind of identities between homomorphisms that we need to use. And so a lot of this stuff indeed can be formulated in quite general setting. So let me make the following remark. So we already considered a notion of a kind of abstract chain complex as a certain sequence of maps between abelian groups define certain properties. So one can consider now a pair of arbitrary abstract chain complexes A and B. This is means we have a for. So what is a chain complex A? This is following data. We have a sequence abelian groups N. And, homomorphisms D. Sometimes if you want to be explicit, you kind of write the dependence on the choice of n here. This is dn, this is d minus 1. But from the context, it's usually clear between which spaces this d acts. So it's usual to suppress additional index for this boundary homomorphism d, and satisfies the condition that the composition of two D's is always 0. So any composition of two subsequent maps D is trivial. And similarly, we have for Bn, and we can write it this sequence exactly above. Sorry, exactly below the sequence of Am groups. And let's suppose that we have a, sorry, this was B, of course, for each in each given index n, it's usually called a degree, as I mentioned before, we have some map from A to B. These are all a collection of homomorphisms. Again, one can write them with some index denoting explicit degree, but it's often to suppress this index and just use the same letter to denote all of these homomorphisms. So this collection of homomorphisms F AN to the N such that the diagram is commutative. So this diagram is commutative, so it's a big diagram, but essentially we have to check for each square. It's enough to check for each square that it's commutative, so that if we go like this, it's the same as we go like this. If the composition of D with F is the same as the composition different order. So such collection of homomorphisms which satisfies this property is called a chain map. So we had a particular example of a chain map where A and B were singular chain complexes associated to two topological spaces, and this F was what we denoted F sharp, the induced map, the map induced from F, where F was a map from X to Y. And we indeed showed that in this case, our F sharp satisfied this property. And essentially, this property was enough to us to define the induced map on the corresponding homology groups. Whenever you have the chain map, which by definition satisfies this property, it defines the induced homomorphism F star from homology groups of the chain complex A to the homology groups of chain complex B. Defined as a kernel of D. Image of D here, D meaning the D acting on a N group, and here D acts on a N plus 1 group. Now here is kernel of D, image of D, and here D acts on Bn, and this D acts on Bn1. So this is why does this work? Because this is well defined because of our property. Chain map. So we define this map as we already did the case of singular chain complexes. So the class, the homology class represented by some alpha. Alpha here is an element of AN, representing some homology class is mapped to F alpha. And this is an element of and if you take another representative, this is not gonna the result will be the same, because if you take if I change alpha by D of something, here I will have F. This will change by F of D of something, and then I can commute F with D operation, And the result will be the change of this guy by d of f of something, which is trivial in the homology. So the argument essentially is the same as well-definedness of the push forward for the singular homology groups, and in that case, instead of a general chain map, we had this map which we denoted F sharp, but essentially the only property we used was this property. Same as before for F sharp. Any questions? Now, also in this abstract setting, we can consider where chain maps so suppose such pair we have a identity similar to what we had before for F sharp and G sharp in the case of singular chain complexes. Suppose their difference can be presented in this form, where for some homomorphism P from AN to Bn plus 1, then such P general setting is called chain homotopy. Between F and G. And again, it immediately follows that the corresponding the corresponding induced maps on the homology groups of these abstract chain complexes are just the same. Again, we did this in the case when we had, instead of F and G, it was we had F sharp and G sharp, and this was D was our boundary homomorphism, and P was our prism operator. And so once we arrived at this property, it was a pure algebraic consideration to show that the induced maps on the homology groups are just the same. So this is so it works the same in these general settings. Questions? So such a kind of abstract general consideration will be useful for us a bit later. And so again, it's kind of useful to separate kind of what parts actually rely on some topology, but what are purely algebraic. So many statements actually will be true in some more general setting. So such kind of more general kind of area is usually referred to as homological algebra. The kind of the area of mathematics where people consider some abstract chain complexes and some chain maps between them and so on. But now we'll come we'll come back to our topological spaces again, and it will be useful to introduce the notion of what is called relative homology. So it may look some sort of as an additional complication. So why do we need this? But as we will see, this is actually a complication, but this will allow to kind of calculate the usual homology groups for some non-trivial topological spaces. So in this, define what is called relative homology, one needs to consider some subspace, let's say A, in our topological space X. And then it immediately follows that the corresponding group of singular n chains of A can be understood as a subgroup in Cn of X. Abelian subgroup. This is just because this is generated by singular simplices with image in A, but of course, since A is a subspace in X, they automatically can be considered as singular simplices with image in X. Gives you a canonical inclusion. And since we have some abelian subgroup, we can always consider corresponding quotient. Abelian subgroup is always normal. The quotient of Cn of X, vector Cn. And such quotient, elements of such quotient are usually called relative chains. Consider chains in X, modular chains in A. And okay, so what about the boundary homomorphism? So we had a boundary homomorphism from Cn plus 1 of X, Cn of X. And it's not difficult to see that it induces the boundary homomorphism on these quotients. Sorry, quotient, yeah, I need to. How do we see this explicitly? Right here. Okay, this quotient, the elements are singular chains, elements of Cn of X, modular elements in Cn of A. So consider some class. So how do we define this explicitly, this D on the quotient? have consider some the alpha in x. So define some class quotient. Take it to a class of d applied to alpha. D applied to alpha is an element in. If I chose n here, this would be an element in Cn minus 1 of x. This its class is a class in Cn minus 1 of x and divided by Cn minus 1 of a. So why this is well defined? Well, let's see. So suppose we take another representative. Say alpha plus beta, where beta is some chain in A. This will be mapped to d alpha plus beta. But d beta will be again a chain. We started with a chain in A in the subspace, then the result of the boundary homomorphism still will be a chain in A, and then it's equivalent to 0 in this quotient. So indeed we get the same. So this is well defined. Moreover, well, once we checked that this is well defined, we automatically see that D, this composition of D with D is still 0. Chain complex. X comma A. So this is this collection of groups C and X comma A forms a chain complex. In the general definition of a chain complex as a sequence of abelian groups and homomorphisms between them. So for any chain complex, we can define the corresponding homology groups. This is what we do here. Relative homology groups. They define for a pair of a topological space X and a subspace A in it. So as for general chain complex, it's a D, it's a kernel of D acting on Cn X comma A. And by definition, it's just a quotient. This modular image of D acting on Cn plus 1. One can explicitly more explicitly describe what are the elements in this kernel in the image in terms of representatives of these elements. In x comma a, in particular the kernel, this kernel which we have in the numerator. They are represented by the classes of alpha. So here class is a class in this quotient, which we consider. So alpha itself is the element in Cn of x. The d so in the usual case, when alpha represents elements of homology of x, d of alpha is just 0 if it's in the kernel. But here, since this is a kernel of d in this quotient, d of alpha is only required to be in n of a. So the class of d of alpha should be 0. This means d of alpha itself should be some element in this subgroup of singular chains in A. And so such chains in A can be called relative cycles. So not as the usual cycles in X, but the relative cycles. In particular, you can consider some kind of schematic picture, how one can understand this. Suppose you have some topological space X, there's some subspace A. And consider, for example, for simplicity, just one chain containing composed of just a single one simplex. Will be example of one chain which is relative cycle. If it's just a single one simplex, it's a single one simplex, so it's just some map from an interval to your x. But if it was the usual cycle, as you know, these boundary points must coincide. Otherwise, so the boundary operation of this gives me this pair of points. It's +1 and -1. This is, for example, alpha, and this is here what we have. Boundary of alpha. And so if these two boundary falls into A, this is CA. Indeed, an example of a relative cycle. It can have a boundary which is non-trivial in X, but the boundary belongs to the subspace in general. Okay, so what about this denominator? How we explicitly describe the denominator? Image of D acting on Cn +1 of X A. Okay, these are represented by let's some classes well, let me take the same simple alpha, where alpha is Cn of x, but again, in the case of the usual image of D just acting on Cn of x, alpha would be required to be a D of some gamma. Cn plus 1 of x. But here, we only care about elements modular elements in Cn of x modular elements in Cn of a. So there can be an addition, let's say beta belongs to Cn. Again, alpha is not a boundary of something, but it's a boundary up to a chain in A. This can be, for example, take essentially the same example where this alpha is not going to be only a one cycle, but also a relative boundary. So such elements in general are called relative boundaries. So you can imagine a situation where these for example, singular one simplex gamma like this. So this is an image of some triangle. And so the boundary of gamma, then the boundary of gamma is this triple of singular one simplices alpha and this guy and this guy. It gives you alpha up to some chain in A. So this is, in particular, this part. This convention here, this part can be beta. Any questions about these definitions and the terminology? So now, okay, if we collect together definitions which we just had, we'll consider the following diagram. So let's consider one place. Let's start with Cn of A. And well, this is a subgroup Cn of X, and one can consider the corresponding inclusion map that's denoted by I. And then one can consider from Cn of X, one can consider quotient map J to the quotient which we, for convenience, denote just Cn x comma A. So this is a canonical quotient of projection map. Mind that this is quotient. And from this, we just consider trivial map to 0. And here we consider, we can extend it to a map to 0. And this is will be an example of a short exact sequence. You can consider similar, similar thing by replacing n with n minus 1. So you have the same. Again, we will denote kind of abuse notations that denote these homomorphisms by the same symbols. But you also have now, if you put it like this, you in the vertical directions you have boundary homomorphisms. All these the columns you can consider as part of your of the corresponding chain complexes. So it's actually you may continue it n minus 2 and so on. So the way we define these things, we automatically get that this diagram is commutative. And again, from so here, so we arrived at a kind of situation where we have a kind of a triple. We have a triple of chain complexes. One is chain complex for singular chains in A. The other is the complex of singular chains in X. And third is the complex of relative chains. And in each fixed degree, they form a short exact sequence of abelian groups. And so this kind of algebraic structure is what actually will be important for us. And at this point, one can consider just a more general setting of this type. Work proofs and prove some statements for this more general algebraic setting, and then use it in our particular case related to topology. Okay, so let A, B, C be the triple of abstract chain complexes. abstract, I mean here just using this general definition of what is chain complex, which may have nothing to do with any topology in principle. Then commutative diagram as I will draw below. So it will be a more general type of a diagram which we have here, but actually rotated by 90 degrees. So so let's start. So the columns, sorry, the rows in these diagrams will be our chain complexes. Okay, the first row is like this. The second row, B groups. And the third row, C groups. Okay, and now we assume that there is in each, if you write it like this, in each column, we have so first in each column we put 0 in the beginning and add another 0, which means trivial group at the bottom. And from A to B group, we have some homomorphism J, and here we have, so here we have I homomorphism, and here we have J, and the same thing for all other columns. Again, this is, of course, these D's and I and J's, they are, of course, different maps because they act in different groups. But for convenience, we use the same notation. Okay, so this is what we need to draw. So, okay, so what is the, I have to finish the definition. So a commutative diagram like this, where all columns are short exact sequences, where columns short exact sequences. Meaning, one explicitly that the remind you what is the definition of this short exact sequence is just that the well, it's, okay, it's short exact in this part, meaning that the kernel, okay, what is meant here, the kernel of this map should be the same as image of the previous map, which is trivial here. So meaning the kernel is trivial. It's meaning that I is objective. Similarly, what does exactness means at this point? So the kernel of this map, which is a whole space, which is the trivial map, should be the same as image of J, and equivalent to saying that J is projective. And finally, at this place, okay, we just have a statement that the kernel of J is image of I. So this is just spelling out what does it mean that these columns are short exact. Okay, so such diagram is called short exact sequence of chain complexes. So what we had before was a particular example of such short exact sequence of chain complexes where our A was a chain complex of single chains in A. So I guess this is a bit might be a bit confusing because here, of course, A denotes a chain complex, and here A here is a topological space in X, so it's different A's. And B was chain complex of chains, single chains in X, and C was relative chains. And again, the I was inclusion, and J is a projection on the quotient. But many statements which we can make, they can be obtained in this more general setting. So, consider. So in particular, okay, let me just announce what we will show next time. So we'll show that if you start with this triple of chain complexes, which can be fit in this huge commutative diagram, then which we call short exact sequence of chain complexes. So this short exact sequence of chain complexes, it induces, we'll show that it induces the long exact sequence of the homology groups. So at some point, you have a chain of A, then you have nth homology group of B, then you have nth homology group of C, and this will be just a map induced by our I, and a map induced by J. So of course, from the fact that this is commutative, it automatically follows that I and J, they're both chain maps. I and J are chain maps. Because for chain map, we just need to show that this the reduced diagram is commutative, which is will be automatic. And then there will be another from Hn of C. There will be another homomorphism, which will construct delta, which will take us to Hn minus 1 of A, and then we'll continue in the same manner. Our next task will be constructing this map delta and ensuring that we have ensuring that this sequence is long exact. Okay. Any questions about today? If not, I stop here.
Thank you, Professor.